The structures associated with water supply and distribution in polygonal complexes have been reconstructed, modified, and restored throughout their entire existence. They remained in demand simply due to their specialization. Everyone who lived in the area adapted them to their own needs in whatever way they could. The functional designation of structures within polygonal complexes is a problematic issue. Hydrotechnical structures, however, are perhaps the only category of objects whose purpose appears obvious. Canals, so-called fountains, underground galleries, complex drainage systems, and many other elements related to water flow regulation are so highly specialized that they seem to serve no other function. At the same time, the preserved authentic fragments of such structures often contain rather peculiar details and structural features. Details that are not directly related to water delivery. Their purpose is unclear and often entirely undetermined. Yet their very existence suggests that these structures were expected to produce something else, something accompanying the flow of water or derived from it. The fact that hydrotechnical structures contain elements unrelated to water supply is well known to anyone interested in the study of hydraulic engineering in ancient settlements. Their presence is usually explained by the idea that these structures were created as an inseparable combination of entirely different aspects, functional and cultural, or functional and religious. This approach makes it easy to attribute all ambiguities to the builder's appeal to something supernatural. This same category includes the alignment of structures with certain astronomical markers. For example, the Temple of the Sun in Machu Picchu is classified as such a structure. This is often used to justify the necessity of sowing fields or harvesting crops based on astronomical cues, following them as divine instructions. One could endlessly debate how much the local inhabitants actually needed such markers and divine instructions for performing everyday tasks, which were repeated and refined year after year, generation after generation. And how rigid such a dependence must have been if it required a substantial portion of resources, effort, and time to create something of this nature. But even if that were the case, it is well known how strictly regulated life in a religious society can be, and no reasonable person would dispute this. The main flaw of this approach lies elsewhere. Religious and cultural aspects of life are declared the primary factors guiding the builders of polygonal structures, while the technological component is considered secondary or derivative. And when analyzing structures composed of parts that differ in their level of technological complexity, this approach fails to provide answers. Moreover, as we will see in the case of Rumikalka, it can lead to erroneous conclusions, and subsequently, to reconstructions that have no real basis. Besides the structures with clearly defined hydrotechnical functions, polygonal complexes also contain constructions of a somewhat different category. One such structure is the Tower of the Sun in Machu Picchu. There is no direct evidence that it belongs to hydrotechnical structures. But this is not because the connection is deliberately concealed or disguised. On the contrary, in polygonal structures, everything is always in plain sight. Such concealment results from technological relationships that are not immediately visible or accessible, Simply because there was no need for direct access, it was not incorporated into the design. And while structures in the first group remain operational, reliably supplying or diverting water, the tower gives the impression that it is now in a state of silence. Its connection to hydrotechnics is revealed only through indirect clues. This is indicated by the attraction of objects and processes directly related to water toward it. It is located in an area where water flows, both surface and underground, undergo certain transformations. For example, the only aqueduct in the complex, upon reaching the tower, suddenly changes direction and redirects its course toward it. From there, it continues as a cascade of 16 sequentially arranged so-called fountains, the first of which is directly adjacent to the tower. A similar phenomenon occurs with the flows regulated by the complex's drainage system. During rainfall, the bulk of the water collects beneath the main square and is diverted toward the area where the tower and its surrounding structures are located. As it approaches them, the direction of the underground streams also shifts, they turn and flow downward. This appears natural, as it is to some extent dictated by the terrain itself. And if one were to map the main water flows in the complex, both surface and underground streams would converge around the tower. From this point, they change course and continue in a single direction. Meanwhile, the rest of the complex, a rather large area filled with various structures, remains outside these processes. All of this could be dismissed as mere coincidences or even as the mixing of unrelated factors. And such an assumption would be reasonable if not for one significant detail. The fact is that the movement of these water flows is not entirely natural. The aqueduct, the cascade of waterfalls, and the drainage system that removes excess water from the complex are all artificial constructions. Accordingly, the water flows within them follow artificially predetermined paths. In other words, within this system, not only have the conditions for these processes been artificially created, but to a considerable extent, the processes themselves have been deliberately defined. And therefore, if a particular structure was built at the intersection of these flows, it means its place was intended precisely there. We will return to the question of a systematic approach to forming the structural foundation of polygonal complexes. For now, let us take a closer look at some details that form the basis of their infrastructure, the details of their hydrosystems. Hydrotechnical structures can be divided into surface and underground components. The underground part consists of water channels running beneath the ground. These are drainage systems, without which no polygonal complex could have existed. The surface part includes open water sources, aqueducts, and reservoirs. These also include so-called fountains, aqueducts, and dams. In a highly simplified form, the water supply system of a complex appears as a three-component structure. At its starting point, there is a source, a stream, river, spring, or an artificial water collection basin, as in Machu Picchu. From there, water enters an aqueduct. The final structure in this chain is either a single fountain, with a small reservoir or cascade of fountains, which may be arranged compactly or spaced at some distance from each other. In more complex cases, such as in Chavin de Huantar, water from one river enters a branched system of underground channels beneath the complex. It also flows into galleries within a structure with solid walls and no windows, fills several open-air reservoirs, and finally, is discharged into another, neighboring river. The channels may be relatively short or stretch for several kilometers. Their width is usually small, 15 to 20 centimeters, but in some cases, it can reach a meter. The walls of most of them are lined with stone blocks with a smooth-facing surface. However, some channels, like those in the famous Cum Mayo, were carved directly into the bedrock. And finally, waterfalls. They are referred to as fountains, but in essence, they are artificial waterfalls with a regulated water flow. Let's take a closer look at them. They may be standalone. These are the most common. Or they may be arranged in cascades. They can be positioned in a row at the same level, as in the Rockchi complex or Ollantaytambo. Or they can be sequential, where water flows from one to the next, as in Wini and also in Pisac. The number of waterfalls in cascades varies. In Tambomache, for example, there are 2. In Wini there are 18, and their technological sophistication clearly surpasses that of most of the surrounding structures in the complex. Where the masonry is authentic and polygonal, the waterfall is either open on all sides or enclosed on 2 sides by low stonework. There are never any coverings or roofs, just as with all other polygonal structures. The main part of the waterfall is a specially crafted block, a shaped outcrop of rock, or a boulder with a carved water channel. Typically, this groove has an oval, rectangular, or trapezoidal cross-section. However, in some cases, separate blocks placed with slight gaps also form the channel. The channel may be open, or closed, where it is covered by a stone block or slab, sometimes also featuring a groove. The vertical section of the waterfall is usually completely smooth, so when the flow is weak, the water simply runs down its surface. Occasionally, the channel extends forward with a small ledge. This part of the waterfall's design is such a distinctive element that it is impossible to mistake it for anything else, even when found separately, with no aqueduct nearby. The number of channels also varies, ranging from 1 to 4. The lower section of the waterfall can have different designs. Sometimes it consists of a platform made of blocks or leveled stones. More often, however, it is entirely carved into the bedrock or a monolith, forming a small basin or reservoir. Their official function is to prevent splashing. This reservoir drains through a designated outlet channel. And if the waterfalls are arranged in sequence, the water then flows to the next one in line. It is common to find niches in the masonry blocks enclosing the waterfall. These niches are generally small and rectangular in shape. An interesting detail is that they are always placed at the junction of multiple blocks. The configuration and number of channels leading water to the drop-off point, their width and depth, and their angle of inclination, all suggest that they were designed to ensure a relatively stable water flow in the waterfall. As we can see, while the principle of operation remains the same, these structures vary significantly in detail. And this variation gives reason to assume that they may have differed functionally as well. In most aqueducts, within channels and waterfalls, it is not difficult to identify sections built at different levels of technological sophistication. This is not surprising. Water has always been in demand. The local population, to the best of their abilities, resources, and skills, tried to keep the aqueducts operational. At times, they improved them according to current needs. As a result, these structures became mosaics. Perfect polygonal masonry coexists with rough stonework, sometimes with mortar and sometimes without. It is clearly evident that masonry made of roughly processed stones represents attempts to modify the primary structure or add some constructional elements to an already existing foundation. These additions do not interlock with the polygonal sections. They are always placed on top of or adjacent to them. In other words, they are independent and somewhat later elements. Nevertheless, this mosaic nature is often interpreted as an intentional decision by the same builders, to emphasize important parts of the structure against a backdrop of rough stone masonry using blocks with precise shaping and fine finishing. It is assumed that those who worked with rough stone could, if needed, also create polygonal masonry. However, simply wanting to create a polygonal masonry section is not enough. Such stonework is not merely an aesthetic choice. It requires specialized knowledge, particular experience, and a unique approach to execution. It represents an entirely different technological level, one that has no points of intersection with rough stone masonry techniques. Nor does it align with the technology of standard masonry using mortar. The difference between these sections is a difference in technological levels. And this suggests that the authors of these sections were likely different. Thus, the purpose of the waterfalls could have varied as well. It is evident that in Machu Picchu, for example, the creators of the waterfall cascade concept implemented it using polygonal technology. Sometime later, other builders adapted the waterfalls to their needs, adding structures made of roughly processed stone. It seems likely that they also modified or adjusted the cascade itself, perhaps even adding something. Some of the waterfalls are constructed at a noticeably lower level of quality. Much more recently, after a long period of inactivity, the aqueduct was partially restored with the involvement of researcher and hydrologist Ken Wright, and the waterfall system was restarted. This time, the structures were restored using modern materials and techniques. As we can see, modifications were repeatedly made to this structure throughout its existence. Both to the structural elements responsible for the utilitarian function of water supply, and to the parts that, in each of these periods, served some additional purpose. Accordingly, the nature of this purpose could not have remained unchanged. This is easy to verify. For instance, today, only those parts of the aqueduct that serve the interests of the tourism industry remain operational. Their functionality is now fully aligned with this objective, to the extent that providing drinking water has become a secondary concern. Several centuries ago, however, the aqueduct and waterfalls reliably served domestic needs, drinking, washing, performing rituals. The cascade was not used for irrigation. Studies show that the terrace agriculture here did not require it, as natural precipitation was sufficient. No water delivery or distribution systems for Machu Picchu's terraces were found during field research. However, it was discovered that another cascade, consisting of 6 waterfalls at the foot of the mountain, is fed by drainage water coming from these terraces. Thus, the challenge was not irrigation. It was quite the opposite. During rainy periods, excess water needed to be diverted to prevent landslides. Since builders working with rough stone frequently added enclosures to waterfalls, making them enclosed or semi-enclosed, it can be assumed that they also used them for bathing and ritual purposes. Some researchers therefore refer to them as liturgical baths, suggesting that the waterfall cascade may have been perceived as a sacred place with ceremonial significance. However, regarding the original function of the cascade, before these additions were made, nothing can be stated with certainty. Except for the fact that the polygonal builders did not construct the same types of structures that later builders working with small, poorly processed stone added to the waterfalls. This means they did not share the same objectives. We can only highlight some characteristics of the original structures that do not align well with the purposes for which later users employed the waterfalls. There are too many waterfalls in one place. They are positioned too closely together to serve only as sources of drinking water. If that were the only concern, they would have been distributed throughout the rest of the complex, yet there are no other waterfalls elsewhere, despite the vast territory. There are also several excessive features if their sole purpose was water delivery. Some of the channels have intricate configurations, and two of the waterfalls in this cascade are positioned directly adjacent to each other. But the most crucial factor is the sections that can justifiably be called original. Those that were built using polygonal technology. If we mentally isolate them, removing the additions of rough stone masonry, they form something cohesive and uniform, matching the other polygonal structures nearby. Uniform in terms of technological execution and even in terms of aesthetics. And most importantly, it is difficult to associate any of these structures with the basic needs of the people who lived here. They were all created within a context that extends beyond what would have been relevant to them. All except the aqueducts. Sections with polygonal masonry can be unequivocally considered primary in relation to other, non-polygonal parts of a structure. The indigenous people treated such artifacts with great care, fully appreciating the quality of the masonry. However, they were more liberal in their use of individual blocks, incorporating them into their own structures whenever possible. Such isolated insertions are encountered regularly. At different times, attempts were made to restore polygonal structures that had been destroyed for various reasons. Sometimes these efforts were successful, but more often than not, identifying restored sections is not difficult. Among other things, these sections tend to have disrupted connections between blocks. Or the masonry consists of separate fragments without proper bonding. Or the walls lack the necessary inclination that originally gave the structure its trapezoidal profile. One example of a structure where large, surviving fragments of polygonal masonry were used is the grand structure at Rumikalka. It is believed to be a remnant of an aqueduct, a part of the water supply system that once delivered water to Pakilakta. It was reconstructed as such, and it is mentioned in scientific literature in that context. The authorship of the majority of this structure is easy to determine. 99% of its construction consists of roughly processed stone. It has no relation to polygonal masonry. However, the end sections of the outermost platforms, where a special water channel was carved into the narrow upper part, are made with polygonal masonry. To understand what kind of structure originally stood here, the best approach is to examine old photographs taken in the early 20th century. As we can see, it hardly resembles an aqueduct. It looks much more like the remains of walls that once blocked the valley at a narrow point. The upper parts of the walls are missing in these photographs. It is impossible to determine their original height. One cannot say how they appeared before they were destroyed. What their upper sections looked like. Whether there was a channel there, and if so, what form it took. It is clear that much of what exists in the structure today is the result of restoration work. Everything except the sections with polygonal masonry. As in Machu Picchu, this structure, in its current form, is the result of 3 waves of construction. First came those who built the polygonal masonry. Then those who worked with roughly processed stone. And finally, in the past century, restorers built something in accordance with their own ideas about the purpose of this site. But let's assume that the restorers were correct. That the channel ran along the top of these walls, exactly at this height, with exactly these design features, and that water once flowed through it. Then why do the directions of the channels on these three platforms not align? This is clearly visible from above. There are minor misalignments in all of them, but one is particularly severe. So much so that the builders had to compensate for it with a special curve. And in this case, we know exactly who these builders were. For an aqueduct, where all sections are within direct sight of one another, such misalignments are highly unusual, if not outright abnormal. Synchronizing the position of the platforms and the alignment of the channels would have required no effort, even without complex mathematical calculations. Yet the direction of the channels follows the position of the platforms. And the platforms, in turn, are aligned with the sections containing polygonal masonry fragments. Therefore, it is far more likely that both when the indigenous builders constructed walls of roughly processed stone and when the modern restorers attempted to recreate an ancient aqueduct, they based their work on the position of the existing polygonal masonry sections. And despite the fact that polygonal structures are typically misaligned with one another, the builders in both cases found it crucial to conform to them. In both cases, the preserved polygonal masonry sections were used as something that legitimized the builders' needs and interpretations of the site. And as a result, in the past century, a structure with water channels appeared here, through which nothing ever flowed. The real aqueduct, it seems, ran slightly apart from this structure. The issue of authenticity primarily concerns the surface components of hydrotechnical structures, channels, waterfalls, and reservoirs. It is far less relevant to drainage systems. This is simply because polygonal structures serve as a kind of marker. Drainage systems are often an integral part of their construction. This is a crucial aspect. It provides insight into the level of organization behind these construction efforts. It helps to understand the sequence of work, from the preparation of underground foundations and the drainage system to the construction of surface structures. A well-designed drainage system is, first and foremost, the key to the existence of polygonal complexes themselves. They were built in mountainous terrain or directly on mountain slopes. Additionally, they are located in climatic zones with heavy seasonal rainfall. Therefore, the engineering infrastructure is arguably the most critical factor ensuring the durability and structural integrity of such complexes. A failure in this system inevitably leads to soil subsidence and landslides, and consequently, to the destruction of the entire complex. Researchers note that in Machu Picchu, for example, 60% of the builders' efforts were directed specifically at creating the necessary structural foundation. The drainage system beneath the main square of the complex includes up to 3 layers of water-diverting materials with varying grain sizes. In some areas, its thickness reaches 15 meters. But drainage also includes special surface channels, a system for draining and diverting water away from structures. In Machu Picchu, underground cavities and caves were also integrated into this system. Its efficiency is such that in 1912, Hiram Bingham, one of the first researchers of this abandoned complex, observed that there were practically no signs of erosion on its territory. And this was after 4 centuries of complete lack of maintenance in an environment with significant rainfall. Such a drainage system is capable of functioning reliably in a fully autonomous mode for many hundreds of years. Human intervention in its operation is unnecessary. On the contrary, careless or uninformed interference can critically disrupt its functionality. There have been cases, such as in Cusco, where underground drainage systems ceased to function due to surface-level reconstructions or other factors. Restoring them proved to be either highly problematic or entirely impossible. This is mainly because the exact location of ancient underground drainage networks is often unknown, or they are physically inaccessible. And sometimes, it is not even clear where their water supply originates. Destruction and subsequent modifications have sometimes significantly altered the original appearance of structures. This applies to canals as well. Many of them were rebuilt using simple techniques and roughly processed stone. The function and authorship of such structures are relatively easy to determine. Their builders deserve respect, but these are clearly much later constructions. A different case, however, is the canal in Cum Mayo. It, too, has partially ruined sections. And sections that have been repaired multiple times. Yet, a significant portion of it has been preserved in its original state. This portion adheres to precise construction parameters and contains structural details that are completely excessive for the simple transportation of water. Their purpose, as well as the effort invested in their realization, extends beyond solving complex but standard problems, such as maintaining a specific flow level and speed or preventing debris from clogging the channel. The canal is approximately 8 kilometers long. It runs through variable mountainous terrain. In some sections, its walls are built from stone blocks. In other places, the channel is carved as a shallow, smoothly surfaced groove in the bedrock. Yet in several locations, as if deliberately avoiding any change in direction, the canal cuts straight through rocky outcrops that stand in its way. And in these sections, the walls rise, conforming to the dimensions of these outcrops. Moreover, these walls are completely vertical, and uniformly smooth across their entire surface. There is no difference between the lower sections, which form the walls of the channel, and the upper sections, which seem to serve no functional purpose. Looking at them, one does not get the impression of a long and arduous process of creating a straight and level channel, followed by careful smoothing of its bottom and side surfaces. Rather, it suggests something entirely different. For example, an effect on the rock mass by something that effortlessly left behind a smooth passage, shaping not only the channel itself but also taking along the excess material above it. The impression left by these sections is, in essence, identical to that evoked by the intricate interlocking joints of polygonal masonry, an unbelievable ease of execution, as if created with a simple gesture. Such processing of surfaces, which do not need to play a role in regulating water flow, is unlikely to be related solely to water supply. It may indicate a specific technique used in their formation. For example, one could hypothesize that a working tool was placed above the rocky outcrop and acted downward, perpendicular to the channel. As a result, the entire affected area was uniformly processed from top to bottom. In some places, the carved sections have a more complex profile. In the lower smoothed areas of the rock, additional material was removed again. This created configurations resembling small overhangs. Elsewhere, the process of carving the passage into the rock becomes even more elaborate. For instance, the canal enters a rock face, makes a right-angled turn inside, and exits from the other side. Such a design is not just excessive. From the standpoint of water transport, it is not only overly complicated but also completely illogical. It would not have been difficult to bypass such rocky outcrops. Yet the canal does not turn away, on the contrary, it appears to deliberately aim for them. It seems intentionally routed through them. When the sole goal is simply to transport water from one point to another, such complexities are unnecessary. This is done when water is meant to acquire specific additional properties, or when something else is intended to be extracted from it. Supporting this idea are sections with small, sometimes unusual changes in the canal's configuration. One might assume these were designed to regulate water levels or flow speed, or that they served as special elements to maintain the channel's cleanliness by altering the intensity or direction of the current. But this explanation is unlikely to be sufficient. In some places, these features are densely packed together, effectively forming a unified structure. For cleaning and regulation, just a few such elements would have sufficed, and they would not have required such intricate designs. Yet, despite these complexities, the canal's width remains consistent, even when it curves or turns at an angle, and the walls are just as meticulously smoothed in the bends. It appears that the canal was not simply meant to allow water to flow downhill to its destination. Its flow direction and intensity were adjusted multiple times, by means of specially designed channel configurations. As a result, intricate flow patterns were created, extending beyond the basic function of water transport. This type of channel design strongly resembles the elaborate, equally excessive curves of the waterfalls in Machu Picchu. And the sudden turn of the aqueduct near the tower likely belongs to the same category. It seems their purpose was the same, to shape the movement of water in a specific way. Additionally, small rounded protrusions can be found on the canal walls, resembling the knobs and bosses seen on polygonal blocks. However, there are differences here. While the knobs on polygonal blocks are typically positioned toward their lower sections, in this case, the protrusions are closer to the center of the canal walls. In this way, they more closely resemble similar features found in some other already familiar structures. Configurations are a frequent, or rather a regular, companion of aqueducts. Formatted rocks and boulders are often found near them and along streams. The canal in Mayo is no exception. Configurations are common around it. Similar features are found in Chinchero. Sometimes, configurations form entire complexes on rocky outcrops and fragments along stream banks. In Kespawara, for example, such a complex is traditionally interpreted as a solar observatory or a gnomon, one of the oldest astronomical instruments. At Urak Rumi, configurations on the formatted side of the structure are also interpreted by some researchers as elements aligned with cardinal directions. The bosses on the structure are likewise viewed as a type of gnomon. However, this explanation is difficult to accept. One could adjust their positioning to fit any convenient theory. Configurations frequently appear alongside waterfalls as well. The facade of a waterfall is often covered with recesses and protrusions of various shapes, step-like or seat-like formations. Sea waterfall cascades are often integrated into larger configurations. This results in a cascade that is visually and structurally connected to various configuration types, as seen in Tombomache or in Tipon. In Tipon, the polygonal part of the complex is largely lost. What remains, masonry fragments, platforms of specific configurations, canals, waterfalls, even individual blocks, has been adapted to the local population's needs. Some elements, such as the large waterfall, were only recently restored. Still, the structure of the complex and its key elements, the platforms and the canal network running through them, have been mostly preserved. Based on these features, it is unlikely that the original function of the platforms was related to agriculture or that the canals were used for irrigation. Their purpose seems to align more with the concept of platforms and polygonal complexes as interconnected configuration systems. Near waterfalls, a specific type of niche is sometimes found. These niches are smaller than those typically seen in polygonal structures and may be either trapezoidal or rectangular in shape. Those who built rough stone extensions attempted to replicate something similar. The function of these niches is also debated. There are two primary theories. One suggests that niches were used to store household or ritual objects. This interpretation aligns with the needs of those seeking to drink, perform ablutions, or engage in religious worship. The other theory is technological. It proposes that the niches served as acoustic devices. Both interpretations have merit. However, it is also possible that they are equally distant from the actual function of these elements. To summarize briefly, most authentic hydrotechnical structures were assimilated by the local population due to their utilitarian value. It is evident that some aspects were borrowed for further use. Fully authentic structures have nearly disappeared. What remains are scattered fragments and details, preserved to varying degrees, and often with an equally ambiguous purpose. However, if we focus on the features that do consistently appear in many preserved fragments, we can say the following. Aqueducts can be considered as specific types of configurations of flow. That is, they represent a dynamic component. They complement the static configurations carved in stone. In this case, the issue becomes more complex and far more intriguing, because it involves the creation and maintenance of an environment with specific properties, through configurations executed in stone and those formed by flowing water. And we have nothing to compare this to. We do not use anything similar.